All right, we want to make our next step with the conic sections and relate it to polar coordinates. And as we relate it to polar coordinates, we then can have the freedom to go back and relate it to parametric equations if we want. Or we saw some calculus with polar coordinates with finding areas within the polar coordinate span of angles, between some angles. We can find areas there, or we can even find arc lengths and stuff. And so I think with the regular Cartesian forms of the conic sections, x squared plus y squared is equal to r squared business, it might be difficult to find areas within those things if we're looking at ellipses or arc lengths of ellipses. But if we're able to change it into polar coordinates, we might be able to find it a little bit easier using some of those formulas that we already saw. So our first connection to polar coordinates is the eccentricity. So the definition of the eccentricity is here. It's the ratio between the distance from a focus point to the graph and that point on the graph to the directrix. And that eccentricity is supposed to be constant. I haven't found a nice picture, graphic picture to try to explain this using graphs and animated graphs, but we could talk about that a little bit later. Yeah.
And so conic section meaning like a cone.
Conic section meaning ellipse, parabola, hyperbola, circles. Those things that we looked at. Things that come from the conic sections.
Oh, from slicing the cone. Okay.
Yeah.
Okay. We're good now. We're back. Back on track.
So I think this is mostly used in astronomy, where when they finally figured out that the Earth goes around the sun not in a circular path but an elliptical path. And they found out a lot of information about that in the sense that, well, that elliptical path, the sun is not right in the middle of that elliptical path, but rather it's what? It's one of the foci, it's one of the focus points. All right? And so they began describing the path of the Earth and for the path of the other planets, for that matter, with this eccentricity. In fact, I think if you look at Wolfram, or not even Wolfram, if you look at any other website, you Google something like, what's that? Popular Wikipedia? If you go to Wikipedia and find the orbit of the Earth there, you'll see that one of the values that they give you is eccentricity. Of course, this one doesn't have the eccentricity. So the eccentricity of the Earth's path around the sun, whoops. Lost it. The eccentricity of the Earth's path around the sun is 0.0167. Okay. So, You know Halley's Comet? That's another interesting eccentricity. Let's call it Halley's Comet. Orbit. Wikipedia. Is it here?
Yeah, on the right.
So eccentricity for Halley's Comet is 0.967, for example. So, do you know about Halley's Comet?
Yes.
Comes around once in a blue moon? No, not in a blue moon.
86 years or whatever. Yeah, 82 or something like that.
Okay. Comes around where?
Where we can actually see it.
Where we could see it. All right. So that's even a different story. But the Halley's Comet is, the orbit of Halley's Comet is an elliptical curve where the sun is another focus point. And if you look at the eccentricity here, 0.96, and the eccentricity for the Earth is being 0.01. Do you have any ideas what that eccentricity is, or what values it could have, or
No.
what? Between 0 and 1, yeah, maybe. At least these two values look like they're between 0 and 1. One's close to 0. The Earth's orbit, the Earth's eccentricity is close to 0, and Halley's Comet's eccentricity is close to 1. Any ideas of how the orbit of the Earth look like? It's close to a circle, so an eccentricity of 0 would probably get you close to a circle, and if you have an eccentricity of close to 1, that would be really a really stretched out ellipse. So Halley's Comet is a really stretched out ellipse.
Which makes sense when you think about it. If we do one full rotation around the sun, whereas that does one rotation around us.
Well, I think it's a little bit more complicated, and it really depends on the path. Path, the speed. So here are a couple of other pictures where Halley's Comet actually looks like it goes out of the solar system, of our immediate solar system. And it's not even on the same plane as the orbit of the Earth, which makes it interesting. So satellites also kind of follow that same situation. Do you guys know how many satellites we have going around the Earth?
Literally.
We have a lot.
Only 12. Amazing. It's definitely greater. Oh.
How do you spell satellite? There we go. We have a lot. So there's a good chunk of them that go around the Earth, and they follow kind of paths around the Earth, and they follow the actual revolution around the Earth. And then there's some that go around longitudinally, and then others that go around kind of around the equator. That's another interesting topic that we could talk about another time. But for now, let's go back to our idea of an eccentricity. And here are some values where E is positive, the eccentricity is positive. If you have a number that's less than 1, it would be an elliptical shape. If it's exactly equal to 1, it turns out that you get a parabola. So imagine Halley's Comet. If you change that eccentricity, it's close to 1, right? So if you change that eccentricity to 1, it'll not be revolving around the sun anymore. It'll break free from the gravitational pull, and it'll just follow a path of a parabola. And a hyperbola If you have an eccentricity that's bigger than 1, then you have a hyperbola. Turns out that we can also take a look at this from the negative side as well. The eccentricities can be negative, except that here it's kind of defined as positive, but we can also look at negative e's when we look at the formula. Yeah.
When you graph a hyperbola, you have two curves.
No, yeah.
How does that happen if you have one orthogonal?
So one, as the object goes around on one path of the hyperbola, it goes to some cosmic infinity and goes back on the other side. That's not really what happens, but mathematically you can think about that happening. It's like having a vertical asymptote. You know, you go down vertical asymptote. My teacher used to say it goes down to some cosmic infinity and it pops up again on the other side. That's just a nice story. In reality, it just you wouldn't see it going on the other side. Yeah, you're only going to see one curve. And realistically, if we're talking about astronomy here, the eccentricity, we would only be concerned about the ellipse and not worry about the parabola or hyperbola. All right, so this is the basic idea of eccentricity, but what we really want to do is be able to play around with it and see what the equation is that we're going to be dealing with. So the equation that we're going to be dealing with turns out to be, well, we want it in polar coordinates, all right? So polar coordinate equations will look like one of these 4 things. I know there's only 2, but the plus and minus will make it 4. So depending on which way your ellipse is going, and I'll focus on the ellipse for a little while there, depending on which way your ellipse is going, whether it's going up or going down, we have this sort of scenario. And the idea is that if you can describe your conic section with a focus point, well, the focus point in this case is the origin, and I want to take a look at graphs of this. The focus point is at the origin, and depending on your directrix, where your directrix is, we're going to see these things change. Yeah?
What's the PF and PL?
Oh, PF is going to be the distance. You have some point. So let's talk about this as an ellipse, maybe. This is one of your focus points, and let's say your directrix is over here. So this would be your point P. This here, this distance here is PL. And this distance is PF. So that's what PL and PF is. And that's to say that these distances the ratio of those distances is constant that goes around. Now, if we had a parabola, then the PF and PF over PL is equal to 1, which means that they're equal to each other, and that's how the parabola was defined from a directrix to a focus point. It turns out that if the ratio is not equal to 1, if it's less than 1, where it's closer to the focus point than it is to the directrix, then those values, the ratios, are going to be constant, and it will look like an ellipse. Okay, so first let's take a look at some pictures of this, and I'm going to focus on the 1 plus e to the 1 plus eccentricity, not e, the number e, but the eccentricity times times cosine of theta. So I'll use a quick graphing program for that. So I'll say R is equal to, and for D, let's just let D equal to 1, our directrix. And let's let our eccentricity equal to 1/2, just for starters. The 1/2 divided by 1 plus 1/2 cosine theta. So this is what I'm taking a look at. I'm taking a look at when D is equal to 1 and E is equal to 1/2, and then I'll just graph it, right? It's the directrix. When I say D is a directrix, it's an equation of a line. So it's either x equals 1 or y equals 1 or something like that.
And that's changes the orientation of your
Yes, and well, not only the directrix, but the whether you use sine or cosine, and whether you use plus and minus determines the orientation. So this is we don't need to do this, but I'm going to put x equals 1. So this is like the directrix. The focus is the origin, and this is your situation. Directrix is a line, yeah. Yeah, you can have it either positive 1 or negative 1. You can have it as y equals to 1 or y equals a negative 1. But again, it depends on which of these functions you're using. So if you're using a sine, then your directrix is probably going to be horizontal. You can, but that's a different story. So if we draw like a quarter of this, pi over 2, you can kind of see where it starts and how it goes. All right, let's take a quick snapshot of this. Add this in our notes that we're not going to understand later on. So as an example, here's our E is equal to 1/2. Your directrix, D, is x equals 1. And then, so this is your ellipse. This is your focus. And we only have one of the focus points, right? And then this is your directrix. Yeah?
Does the equation, the polar equation, is that formula like kind of derived from the, a formula from the Cartesian formula?
It's actually derived from here. And so what they did was they I'm not going to do it. You can look in the book. They looked at the distances, and then the distances between between these things. They made triangles, and they made trig stuff. We don't need to worry about it. All right. So so let's see if we can draw the path of the sun, or draw the path of the Earth around the sun using our eccentricity. We need to know a couple more things, though, based on this information. well, it would be nice to know where it crosses the x-axis, right? And depending on what your directrix is. So I think we're going to need to figure out some. Well, I guess before we do the Earth business, let's do some practice problems. I was looking at these types of problems where we're finding polar equations of conic sections. So let's pick a problem between 1 and 8. 5. So it looks like they gave us the point in r theta, not in xy, so we should be able to read that appropriately. This is your r and your theta. So what's that look like on the graph? So, well, first of all, it's a parabola, so we should know what the eccentricity is, right? What's the eccentricity? E is equal to 1. So let's keep that piece of information ready for us. 4 comma 3 pi over 2. An angle of 3 pi over 2 takes you where?
The lower y.
So an angle of 3 pi over 2 will have you pointing down. And an r distance of 4, 1, 2, 3, 4, puts you here. So this is the point 4 comma 3 pi over 2 in polar coordinates. Now, what other things did they say? Did they say where our foci is supposed to be? I think the foci is supposed to be at the origin for this thing to work. With the focus at the origin in the given data. So the focus point is going to be at the origin, and this is your vertex. So you want your parabola to be going up this way, and your directrix should be down. It should be on the other side, right? So it looks like one way to do this is to just use some equations and what you know about this. It's what?
Yeah. For the directrix.
So directrix is the equation y equals to -8 because it's the parabola, that's your eccentricity, and it's going to be the same distance directly along that line. So I think we have everything, right?
Yeah.
Plug and play. So R equals your eccentricity times your directrix divided by 1. Now, this is a plus, is this a minus, is this a sine, is this a cosine? How did you get plus and a sine?
The sign because you have the sign because you have the directrix of y.
So sine because it's a directrix of y.
And then I'm just getting positive opening up upward.
All right. Well, we'll see. We'll check it and make sure. So this thing is the 1 plus e times the trig function, right? So e again is equal to 1. So we'll drop that there. As your eccentricity. All right, so you take out your calculators and plot it and see if that's exactly what you would get. Let's see what happens here. So we got a -8, 1 plus sine theta. All right, so if you mistook this for a negative sign and you got your graph going the other way, just change it to positive. But sine generally goes up and down, and cosine generally goes left and right. Okay, so that goes for hyperbolas and parabolas and ellipses as well. Okay? Guess we don't need a picture of this. Oh, by the way, the graphs are being drawn in a certain way. So what if I just want this small part of the parabola that's below the x-axis? How should I change my theta limits? I go from 0 to 2 pi, and then I get this whole parabola. What if I want a piece of the parabola? Pi to 2 pi? What?
So pi to 2 pi actually is this all half.
Pi to 2 pi?
0 to pi.
If I go from pi to 2 pi?
Oh.
So what should this be? 0 to pi?
Yeah.
So it's like a guess and check.
Okay, so that's another good question. Which way is this being drawn? We have our drawing ray.
It's a negative 8, right? Was that affected?
Right, it's a negative 8. So let's see how this is going to be drawn. Our drawing stick. That's what we called it.
Yeah. Really starts making the tricks.
So when I guess I should make this longer. When theta is equal to 0, I'm pointing in this direction, right? And when theta is equal to 0, sine of 0 is 0. What do I have?
-8
Minus 8. So I'm actually starting over here when theta is equal to 0. Does that make sense? Now, as I turn, and by the time I get to theta is equal to pi over 2, theta is pi over 2, I get sine of pi over 2 is 1. So I get negative 8 over negative 2. So I'm at negative 4 down here. And then as I continue on, I'll be on the other side negative. So this thing's continually going to be negative. And when I'm at whatever this angle is, what is this angle? 5 pi over 4? When I'm at 5 pi over 4, I'll have some value over here that's going to send me as part of the parabola over here somewhere. Right? And then if I go to 3 pi over 2, what's sine of 3 pi over 2? Negative 1. And what's this expression going to be? it'll be 0 in the denominator, right? And so there's nothing up here. So this parabola breaks off, and then there's nothing over there. So it draws it over here, and it goes off to infinity up there. And then it snaps off. That's like breaking the orbit from your ellipse. It's a parabola. Okay? That sound okay? Yeah.
It stops there and then continues right?
Well, it doesn't stop here at at 3 pi over 2. That's when it goes to cosmic infinity, and then it comes back down over here, and then continues to draw it on the other side. Are you guys cool with cosmic infinity? All right. What?
Would we ever have to find like where it breaks off?
I suppose maybe. Yeah, in this class, probably not. But in real life, I don't know what real life is anymore. Questions? Okay. So that was fun. Let's see if we could do another problem. Number 14. So here they actually gave us the equation, although it doesn't look like it's a nice equation where we can, there's an E and a D and stuff like that. And because 8 is 8, right? It looks like that should be your E times D, but the 5, maybe that's your E. I don't know. What does that formula say? What is distinctive about that formula? What? It has to be a 1 plus or minus something. So in terms of having a polar coordinate equation like this, and you trying to relate it back to eccentricity and directrix and all that, your main goal is to make this into a 1. Okay? Currently it's a 4. We want it to be a 1. So how are we going to make that into a 1? So all this is a bunch of algebra. And what we'll do is we'll factor out a 4. There, now it's a 1. But when you factor out a 4 out of the 5, it's not a nice thing, right? So it's 5/4 sine theta. So this 4 can just get absorbed with the numerator, and you got 8 over 4, which I think is a 2. So according to the formula, it looks like you have your eccentricity already identified, but your eccentricity doesn't look like it lives up here yet. So what you want to do is do one more little massaging thing. And you want to know what you multiply 5/4 with to get 2, because that's what this value is. Right? Is it 2? Yeah, it's 2. So, yeah, what do we multiply 5/4 with? Probably something with a 5 in the denominator. I don't know. What would you suggest? 8/5 would work? Or you could do 2 divided by 5/4. And so now if you write your equation like this, you have your eccentricity identified, and you have your directrix identified. And now you look at the sine, right? It's not a cosine, it's a sine. So what's the actual equation of your directrix? It's what? It's a y equals to 8/5. Okay? So, is this a hyperbola, a parabola, or a ellipse? So E, bigger than 1, so it should be hyperbola, right? So we know that this is a hyperbola. the directrix is a positive value. Hyperbola opening up and down or left right? Up down. So it'll probably going to be something like this. And then we have a directrix of 8/5. So one of the focus points is probably going to be up there, and then we'll figure out the rest in a minute. But is this okay so far? So is the algebra okay? All right. So what are we supposed to do for this problem? We're supposed to find eccentricity, identify the conic, give an equation for the directrix, and sketch the conic section. So we just, is this a good enough sketch? All right. The foci is going to be at the origin. And we have the directrix up here, 8/5, so that's a little bit less than 2. Oh, so it actually should be like this. So let's figure out where this thing crosses the x-axis, or the y-axis. Let's figure out where it crosses the y-axis. This is your x, this is your y. And any ideas on how to find that point where it crosses the y-axis? Let me give you a couple of points here. This is the point 0, 0, that's the origin. And this would be the point 0, 8/5. That's how the polar coordinate conic sections are. The foci is always the origin. Focus foci. There's another foci up here. But halfway?
But it's equal distance, isn't it?
If you have a parabola, then it's equidistant. Do you remember? But that's the key, is to find a distance from the focus to the graph and the graph to the directrix. And what is it? Yeah.
We use the ratio of eccentricity.
So the eccentricity, if you remember, is the ratio from the distance, it's the ratio of the distance from the point to the focus divided by point to the line.
Oh, line.
So let's see. The distance from a point to the focus is, I don't know, what's that point? Oh, that's what we're looking for. Should we call it, let's call it P, little p. So the distance from the focus to that point would be the distance between 0, 0 and this point P, which should be what? P. And then the distance between that point to the directrix is what? 8/5 minus P. What's the eccentricity again? It's 5/4. That's what the eccentricity is, 5/4. We can do this, right? We're all big now. We can solve for P. Solve for P and tell me what you get. All right, multiply the denominator of both sides, or you can even do the cross, what's that thing called? Cross multiply. Oh, you can do all kinds of stuff. I plug it into Wolfram Alpha. I'm just waiting for somebody to solve for this. Somebody going to solve for this, or are we just going to talk for a little bit? Is Jessica the only one solving for this? What? 8/9?
That's a reasonable answer.
So we're going to agree? All right. So then that's your value, 8/9. Point itself is 0, 8/9, yeah. So if you want to find out where this crosses the y-axis on the other side, it's just a distance from...
Yeah. No, I would think that they would be equal distance away.
I don't know.
That would make reasonable sense to me.
Then again, that is not
All right. Well, probably. So let's just...
Hyperbolas are symmetric though, right?
yeah, they're symmetric. But I don't know if the directrix is a symmetry. Pat? All right. Well, let's graph it using our handy dandy...
How do you do it?
So no negative. And we have a 4 plus 5 sign. Oh, let's go all the way from 0 to 2 pi. Oh. Y equals, what is it? 8/5? Yeah, so it's not symmetric. But if you have one of the vertices, you should be able to find the other stuff using the other formulas for for the graph.
So that means that the directrix is only for one, like, hemisphere of the hyperbola.
Yeah, the directrix with its associated focus point is dealing with just one side. Okay? Any questions? Yeah.
Is it possible to have more than one directrix then for a problem like this?
Well, if you have an ellipse or a hyperbola, then you have two directrices. Yes.
So these shapes all come from slicing a cone, right?
Yeah.
So how does the directrix relate back to the cone?
Oh, I don't know.
Oh,
That's a good question. The answer is I don't know. All right. I wanted to show you guys a little animation thing, but I don't think I saved it.
So when it says graph it with the directrix and the eccentricity of only one hemisphere, that means only graph that southern hemisphere or whatever? Because it's only that directrix for that
Yeah.
hemisphere. Okay.
No, you should graph both.
Yeah, if you have no information, yeah.
So,
Yeah, just use graphing.
so this is kind of cool. Where is it?
Oh, you do it for E. Yeah.
So if I change the value of E, I'm calling it N up here, and I'll say assume that directrix is equal to 1. This is how it would look like. So this number down here is the value for E, and because it's being scaled also, it's a circle of radius 0 right now. But if it starts growing, you see that ellipse, and as the eccentricity gets closer and closer to 1, so 0.99, let's see if we could zoom out. It still curves back down as an ellipse, but once you cross over that 1 threshold, I can't get exactly 1 apparently, then it starts becoming a hyperbola or a parabola, and then onto the hyperbola. And then if you change your hyperbola. So this is a little animation that looks kind of cool. And then in terms of it going on a negative direction, you could actually have it go in a negative direction, and all that's going to do is going to draw your directrix on the other side. I guess it didn't. Let me just fix this to 1. So then it'll go on the other side. That's pretty cool, huh? So at 0, at the very middle point, is when you get an eccentricity of yeah, so just imagine how this would look like if n was equal to 0. What's r equal to? 1. So r is just unit circle. Yeah. Okay. All right. What else? The Earth. Halley's Comet, the Earth. So let's take a look at this information about the Earth over here. With I want to focus on the eccentricity and semi-major axis. And all that business. And let's see if we can come up with an equation. What's AU?
Definitely not. Definitely not.
Maybe we should go metric here. Can I change metrics? I don't want to see metric. I want to.
I think it's too early late.
Yeah, that would make sense. What is the distance to the sun? So, yeah, it's just a number. What is it? Billion?
Billion. No, it's million.
Million.
It's 92.9 billion miles.
92.9
billion miles.
billion. So this is 1 AU, right? All right, let's see if we can find that equation. So we need to translate this, the semi-major and semi-minor axis. So I think what that is that distance that it's going to cover over here, the semi-major axis, is going to be 92.9 billion. Let's write this in scientific notation. This is 9.29
Wow.
times,
At least I fixed it.
so 6, and there's one more, 7, 10 to the 7th.
Yes.
That right? Come on, you guys are engineers, right? Wanna be? So let's say that this is going to hit that axis there, and we have the eccentricity of this thing as 0.01. So we need to find a directrix. And we'll assume that the directrix is going to be over here, since we're laying it out as, we're going to lay this out as R is equal to, what is it, E times D 1, and let's use the cosine function. So the distance from the sun to the earth, if the earth was over here, would be 1 or 9.29 times 10 to the 7th.
I think it's, yeah, to the 9, or the 10. 1, 2, 3,000.
This is million now. She changed it to million.
Oh.
Million. So now is it okay? Is it to the 7th? Okay. So I need to figure out this equation over here. So this is an x is equal to some value. What's the value of this thing? Remember how to find that directrix? So this is an ellipse now, right? And we're looking for a couple of distances here. This is a point. The Earth is going to be at this point when it's directly opposite from the sun, and then you want the distance from that point to the line. So I think we call this PF and PL. And eccentricity is equal to, is it F over L, PF over L? So PF over PL. And our PF, this distance over here, we said is 9.29 times 10 to the 7th over PL. So this is a distance that we're looking for. And the eccentricity is 0.0167. All right, so we need to find out what the question mark is. And then after that, we have to add it to 9.29 billion or million. So what is this question mark? Okay. So that sounds about right. This is actually 1.6 times 10 to the negative something and negative 2. Okay. So this number, is that what x is equal to?
No,
What is this number equal to?
the distance from.
So this is PL. And so if we want x equals 2, what do we need to do? So PF and PL. So you got 9.29 times 10 to the 7th, and then 5.56 times 10 to the 9th. And what is that finally going to equal to?
5.66.
So that's our directrix. All right? So now that we have that, we could just plug it into the formula. So our R is equal to the eccentricity 0.0167 times the directrix, which we found to be 5.66 times 10 to the 9th power, divided by 1 plus 0.0167 times cosine of theta. So if we graph that, we should get the thing, the path of the Earth. Yeah?
Yes.
So let's take a look at the graph, and let me scratch off the 10 to the 9th, because that might get too big for my graphic. Actually, I can leave it there if I want, but so let's see. This thing should be close to a circle, and why don't I just put 0.0167 times, I put 5.66, and let's scratch out that other factor that'll just make it too big. And then my value coefficient of the cosine would be this. Oh, it looks so small. Let's multiply it. Now it looks too big. Oh, there it goes. That's it. That's your Earth revolving around the sun. It looks circular. That's why it was a little deceiving that it, wasn't really circular. Okay. So one interesting thing about this, and one of the reasons why they studied this in polar coordinates, ellipses in polar coordinates, is because Mr. Kepler found some interesting relationships between the orbit and some facts about ellipses. So I'm not going to go through all of this, but I do want to highlight the second one. The line joining the sun to the planet sweeps out in equal areas and equal times. And for this, we kind of need to go to parametric equations. Maybe I'll have that as a special problem for you guys to do. Is to go into parametric equations where t will actually represent time. And so we can put factors of t and make sure the sun goes around the Earth in 365.25 days or something, whatever it is. But just this idea that it sweeps out an equal amount of area within your ellipse is in itself like an interesting property of an ellipse. So what this is saying is that if this is a sun and this is the Earth revolving around the sun, say in 2 months' time, the Earth would sweep out this much area. And then in another 2 months' time, the Earth will sweep out this area. And what they're saying is that if this time distance, not the length of the curve, but the time it takes for the Earth to go from here to here, let's say we're close to the sun, so this would be summer, right? Ish. What's after summer? Fall? So sometime in the fall, sometime from...
That's why we seasons? I did not know that. Holy crap. I didn't know that. Come on. I don't know.
So this this around the fall time from September, October, November, from September to November, the area that the Earth swept out from the sun would be exactly the same as it is from, let's say, from February, March, April to April. No, the arc lengths would be different, but the areas would be the areas not underneath, but the area to the sun would be the same. So equal areas. Being swept out at equal times, so 2 months. And so having this in polar coordinates would be easy to find if you had we have the equation in polar coordinates. Having this in polar coordinates would be easier to compute because we have a nice simple formula for the area in polar coordinates, right? You guys remember what the area was in polar coordinates? Just if I were to give you a pop quiz. 1/2 r squared d theta and integral from alpha to beta. Right? So different time segments now would give you should give you the same value as long as those times that you're taking are the same. Okay? All right, so I don't know what your homework is like for this section, but I hope there's enough information here to get you through the homework. I am interested in having you guys, just for fun, I don't know, extra credit maybe, try to figure out the path of Halley's Comet with an eccentricity of like 0.97 or whatever it was. And if you find a distance, the closest distance from Halley's Comet to the sun, whatever that value is, closest distance, that can measure your your major axis and then try to figure it out. Oh, it's a book problem, yeah. So another thing, you guys know about the shooting stars? You know what they're about? So what happens is that there are these comets that fly around all over the place, and so as they fly, they leave particles behind, right? So at some point here, they left a particle behind. Maybe the comet's way outside of the Earth's orbit, but along the Earth's orbit, the comet would have left some particles behind. So when the Earth passes through the path of a comet, all those particles that are left behind gets kind of ruffled through the Earth's atmosphere, and then so that's why it looks like shooting stars, is because the Earth is moving. The particles are just sitting there in space. The Earth is moving towards it, and so you can see all those things pass by like it was actually moving, where it's not the particles that are moving, it's actually the Earth. Pretty cool, huh? Yeah. All right, good luck with your homework.